All right. So there's a couple of things we need to take stock. So at this point, don't raise your hand. Just yell anything. We'll try to figure out what we have in the way of hardware to deal with. So how many people have some access either through the network or not through the Institute's parallel Tesla card to a GPU of some kind? Okay, and now of the rest of you, are you expecting to use the Institutes or just background? Yeah. The problem, a major feature / bug of these devices is they're very unhappy if two users try to use them at once. Okay? And we discovered this by having a bunch of grad students working at random times, and the codes would work some days and not others, and it took us a while to figure out that the somehow fundamentally on the graphics processor, it's just not real well designed for multiple users. So that does not affect in the least compilation, which is part of what we're going to talk about. But if you're sitting there and you're trying to run a CUDA code on, how many of you are going to run it on your own laptop? Okay, you're fine. How many of you would run it on a computer back in some other institute that you know has an appropriate GPU in it? Anybody? Okay. Of you, do any of you know that nobody's sitting at the console right now? So you do know that it's good. Does anybody have the situation that somebody might sit down at the console while you're trying to do something? Okay, good. The kind of things that happen when you do that, it may nevertheless happen to you. So let me just tell you the symptoms. You get a total freeze and just nothing. And you have to do a hard reboot sometimes if there's an interaction between a person sitting there and a person trying to do the computation. So try to avoid that situation. Okay, how many of you are using the Tesla that's here on site? Okay, just a 2 or 3, 4, 5. Okay, if you're doing that right now, I don't think it's batched. Is that right, Peter? It's not a batch job driven thing. Okay, so I would advise you not to try to run while we're in this group dynamic on the common GPU that we all have available to us. What you should do, if you're sitting there with your laptop and you want to do something, is work on compilation and other things, and then we're going to have to sit according to computer we're using so that if 2 or 3 of you are trying to use the on-site GPU, you can say my turn and so forth. Otherwise, it's going to be a hard reset. Somebody will have to walk over, go to the basement, find the thing, and turn it on. Okay? Yeah?
Wasn't there an option to run it in dry run mode where you can emulate that so at least after you compile it, it's fine. There's a dry run mode, I believe.
Yeah, there is an emulator. That's right. I haven't used it much because we were pushing hard last year and the emulator didn't work very well. But yeah, we could do that. The fun is seeing things go fast, of course. Okay. So here's what I propose, and I am open to suggestions. What I propose is, how many of you have NVIDIA, but you don't know what an SDK for NVIDIA is? Okay, good, honesty. How many of you have NVIDIA, but you've looked at the SDK? Okay, minority. And how many of you are interested in GPUs that are not NVIDIA right today? One. Oh, good. So tell us which ones. Oh, no, if it's on your Apple, you have OpenCL? Is that the thing?
Yes.
What about you? Yeah, sure. Well, there was a couple over here. Yeah. You've got an ATI and you've got what? Okay. What's the ATI language right now? Brooks? Is that? Okay, I don't know either. Anybody else? Other machines? Is anyone here using a cell? Next Friday, there's a speaker who was added to the program towards the end who is going to show you truly astounding results based on the cell processor, which is the PlayStation 3. really world-class stuff. But I haven't used it. That's the Roadrunner at Los Alamos. Okay, so here's what I propose. If you're sitting here and you have in front of you a computer that has NVIDIA hardware and you're interested in this stuff, take this time to sort of halfway listen to the things I'm talking about and try to get the thing loaded onto your computer. Okay, you follow the directions there. And so you download it, and you want to find a you'll know you're happy when you can find a directory that's all caps SDK, all right? And it might be NVIDIA_SDK. So I'll check back in with you in a few minutes, those of you that have not seen that yet, because the secret to getting started on this machine is the compilation. Compilation is once you're used to it, it's fine, but it's complicated. I'll talk about it in a minute. But so the SDK has all the compilation secrets in it, and all of the clashes that'll happen between your compiler and underscores, all these things that can go wrong that we've seen on the Google Groups will begin to be addressed if you've got the SDK, if you've got things loaded to the point where there's an SDK in front of you, and then we can do a compile line and do a hello world. But until then, it's very hard. Are you doing OpenCL then? Aha. By the end of this session, we will have all the laptops broken, so that's fine. What? Okay. OpenCL, how many people are interested in OpenCL? I can say, all right. I'm terribly interested in it. Here's what I've learned so far. We looked at it, downloaded it, played with it a little bit. It's coming out tomorrow or yesterday or something on the new Snow Leopard, all the apples out there. And my experience so far is, I'll show you some examples in CUDA. If you want to do something in CUDA like declare a procedure is going to run on the device, on the graphics processor, using global memory or something like that. It's going to be called from the host. This is a simple bit of text, syntax in CUDA, and a rather larger set of syntax in OpenCL. And so what I would like to see come out of OpenCL in very short order is that somebody says, you know, this is too general. This language is giving us too many hooks to too many things, and we only need about 10 or 15 concepts from OpenCL. And it would be nice to have someone figure out what those 10 or 15 things are and then wrap it up. And I can talk about that if anybody's interested. Okay, so these are slides that come from the course that was taught at Maryland by Ramani Duraswamy, who took the slides from a course at University of Illinois, Urbana-Champaign, by Hu and Kirk. And Kirk was the, if I've got my facts straight, was the chief scientist at NVIDIA until very recently, and now the chief scientist is this guy from, there it works, from Stanford. So Kirk was an expert in graphics, is an expert in graphics, and really brought the GPU up for its graphics processing. And now they've got a new chief scientist at NVIDIA who's from the parallel computing world, because they're really aiming at people like us. So this is a good thing. And that's this Bill Daly guy. Okay. So this is rather general stuff, and feel free to interrupt and take us in any direction at any time, okay? I'm just trying to give you some information. So you do your writing and analysis of your software on the CPU, which is often referred to as the host, making the GPU feel like a parasite to me, but that's just my feelings. So this means that you have to deal with the programming environment that you've set up, inadvertently or on purpose, and the compilers and libraries that you're dealing with. There is a profiler if you've got a reasonably recent version of CUDA, and there's an emulator, as Peter said. And so what you end up writing, let's see. How many of you are dinosaurs like me and use Fortran? Ah, beautiful. Okay. So none of this is good for you. but we have to deal with the C world because I'll explain it to you. So the NVIDIA gives you a new compiler, NVCC, NVIDIA C compiler, or NVIDIA CUDA compiler, I guess. I'm not sure which one it stands for. But the invocation line is NVCC. And NVIDIA's that compiler can recognize C code for what it is, and CUDA, which is that extension of C, which it knows how to drive the CPU, is a very mild extension of C. It's non-standard. It's not standards compliant. It means you can't compile CUDA code with anything except NVCC, but you can compile any C code with NVCC just fine, right? It runs in that direction. So what you end up writing, those of you that are in the C or C++ world, is C, and preferably C, not C++, with embedded GPU routines in it. And all of us, whether we're in Fortran or C or Java or MATLAB, whatever, will know that there's a set of precompiled, which of course you've compiled, libraries on your available to you that came with the CUDA library that have things like the headers for math functions, FFTs, basic linear algebra subroutines, and so forth. So there's level 1, 2, 3 BLAS is all implemented on the GPU in a fast way. How many of you think I just spoke Martian? Who knows level 1, 2, 3 BLAS? Okay, I won't say those things again then. Things like y equals ax plus b and simple statements like that are already available to you as function calls, and that's called the basic linear algebra subroutines. And there's levels 1, 2, and 3. This goes back to the ancient days. There's levels 1, 2, and 3. Level 1 is really simple stuff like a equals b plus c, that kind of stuff. Level 2 is a little bit more complicated, and level 3 is a little bit more complicated. But they're all available, and the levels really don't matter to you. It's just you have to look through the BLAS owner's manual, and you'll see, oh, if I need to do that, I can call this library subroutine. Okay, so we all have access to the library subroutines. You're going to write some C code, and we're going to have some GPU code. We feed all of that into the compile line, NVCC, and that will produce assembly code. You don't need to know this part now, but just to let you know. It produces the appropriate code for the GPU. There's profiling information, and there's some basic information which I'll describe to you about register use and other things like that that is given to you at the time of compilation. And then there's a bit of code that actually will be the kernel that's going to run on your computer. So let's see how that stuff works out. Here's a flow chart. So you have your source code on the CPU, and you can have part C, part CUDA. These are mixed together. When you run NVCC, that'll separate out the CPU code and just hand that over to whatever C compiler you've set up on your machine. So if you've been using GCC, it hands all the C over under the hood. You don't need to know, but it's good to know what's going on. Under the hood to GCC, or if you're Windows World, Visual Studio. Then the libraries are set. Actually, this is not sequentially. In general, there's a bunch of CPU environment variables which are set, and the GPU code is compiled on a GPU assembler. That produces some of this PTX code, which then gets spit out for the individual GPU that you have on your machine. And again, you don't need to know that step very much. I tend to ignore that kind of stuff. Let me see what the catches are here. Okay, so for those of us in the Fortran world, okay, first, C world. There's two interfaces to CUDA. There's something called the driver interface and the runtime interface. And these are both what are called APIs, right? So that's the front end that you see. You have to pick one, typically. And there's not a good rule. I tend to get them, I use both, and so I get this confused in my head. One of them is basically a higher level, restricted functionality, easier to use, and I believe that's called the runtime API. And the other one allows you to do anything you want, And so instead of just saying a simple invocation line, you might have to add a couple of extra variables to specify a simple function, but you have complete control over things, and that's, I believe, the driver API. So you have to pick one. You can change later in life, but even if you're here and you end up getting Hello World working tonight, and you want to write a little bit more complicated code, and you look in the SDK, so, okay. Those of you that didn't have the SDK, do you know what an SDK is? Okay, good. Does anybody not? Okay, it's Software Developer Kit. And it's very common these days when you get a new widgets for your computer, they come with a bunch of SDK software, and basically it's examples. Examples of anything that you would like to do are often available in this SDK. So once you get an SDK in front of you, go into the subdirectories, and you'll find code for finding the maximum value in a large array. You'll find code for multiplying two matrices together. You'll find code for XYZ. Whatever it is you want to do, there's examples there that you can go all the way from make to execution and do a timing and see how fast they go without knowing what's under the hood. So the SDK is really valuable. Far more important is when you want to start writing code, you can look at the compilation stream that exists for each and every one of the SDK codes that comes in the kit, and you can understand how you're supposed to set up the environment variables in Link. We'll do that in a minute. But be aware of, yeah.
For those of us who want to do multi-color simulations, is there a parallel random number generator available?
Parallel random number generator? I believe the answer is yes. I'll find out for you at the break. There's certainly, what I don't know is the quality of it and whether it's intrinsic on the hardware or somebody wrote a simple one. Okay. Here's the kinds of extensions that exist. You have to, there's some new declaration specifiers. There's 5 of them. This has to do with your memory that I was talking to. Yeah. Well, I attempted to maximize it, and we got this. If I push green,
there's a full screen on the menu.
I tried that. Show me. I mean, just tell me if you see it.
Maybe under view, slideshow.
It won't go to the next page if I do slideshow.
Use an arrow or the menus. Yeah.
See? Click, click, click.
Hit play, and then
Yeah, but then,
What about trying to use the arrow on your keypad?
see, it starts going.
Stop the play.
Oh, I see. Okay, so we'll just start and go. Okay. That won't go. Oh, you guys are geniuses. I've had apples for years. That's just great. And you're looking for me to advise on how to run CUDA? Yeah. Thank you. Okay. So there's these different kinds of specifiers for the variables. It can be a global variable, device variable, shared, local, constant memory. We'll come back to these things. There are keywords, which are predefined in the language, thread index and block index. Before we get into the specifics of how CUDA works, you can imagine that if you're doing a graphics calculation, you are dealing a lot with 2D arrays, and at every point there's some vector amount of data, which might be a 3-element vector for how much R, G, and B, and then a 4th element, which is overall intensity, right? So graphics processors naturally have vector information stored in 2D arrays native, okay? And so what you want to do when you're writing code is be aware that such things were coded a long time ago for the graphics guys, and just assume that there must be a clever, fast way to find data in such a structure, and there is, right? And in this case, it has to do with the threads and blocks, which have to do with, we'll do the details another time, finding yourself in this 2D array. There's intrinsics. This is like a call barrier if you're an MPI person, but it's not equivalent, but it synchronizes some threads. In the runtime API, there are some issues with dealing with allocation of memory on the device, and these look different in the driver API. Okay, so there's common familiar variables for the C crowd, like memory allocation, malloc, and then they just stick the word CUDA in front of it, and that's going to do the same thing on the graphics device. And finally, the other major one is this triple, they call it chevrons, less than, greater thans, that indicates that you're launching a kernel. And so this one has 100 blocks with 10 threads per block. So there's something that's been made called convolve. Somewhere there was a void convolve, which has a bunch of things in it that is presumably going to convolve two sequences together. Pardon me? This is to call it, okay? And so it's going to call it with 100 blocks and 10 threads per block, so chunks of 1,000, yeah. Whew. I believe at the current time that the answer to that is yes. But I have seen long talks where people worry about whether they ever need to vary these to get good performance. And fundamentally what people have done is there's some sizes which are big enough to get very good parallelism if your problem's bigger than a certain size, and then 10% changes if you vary those things. So in practice, I've never varied them. All right, I have to do this here. Great. Okay, so what are the blocks and threads? They look like this. There's a host, so this is your CPU, and the host is going to have some functions, which are called kernels. So there's maybe this kernel and this kernel. Each thread is going to use these IDs, which are intrinsics, block ID and thread ID, to decide which of the data sets to work on. So it can be, the blocks can either be in one dimension or in two dimensions. Of course, everything is laid out linearly in memory, and you don't get to see under the hood, at least I don't remember ever seeing under the hood how the stuff is actually laid out on the chip. But if you declare a 2D array, you end up the 0, 0, 1, 0, 0, 1, 1, 1, and so forth. So there's a grid with blocks in it, and then inside each block, there's a whole bunch of threads. And the threads can be indexed with one index, 2, or 3. And this is just really copacetic when you want to deal with large 2D, 3D data sets. If you want to do a 4D or a 5D data set, which is what I deal with, it's a real pain in the ass because it doesn't come with a 4D or a 5D data set. So you end up building your own intrinsics to find data inside that data structure of a different dimensionality. Those games can be played, but this is the basic layout, and those are intrinsics. Okay, here's the basics on memory. So you can allocate, you give it a size. I forgot. Oh, memory. What is memory set in C? Does anybody know? Right. Okay. So the Fortran version of all this, we have a different name, right? Okay. So allocate the memory, fill it up with zeros, presumably something else if I want to put it there. Is that the idea? And then free the memory. And so you could say I want 1,024 integers, ints, and we'll start with them all 0, and this is what it would look like to allocate it, fill it, and then let go of it. So it looks like C. Okay. This gets a little bit tricky. Let me think. Right. So you can copy one direction or the other. And before we get into, I don't want to spend all of our time only on CUDA. There's some generic things that have to be done. You have a device with its own memory that's external to the CPU and does not have access to the RAM on the CPU. And so there has to be a call that says, find a piece of data and put it over on the other device. And that's host to device, and there's device to host. I don't know about device to, oh, that's just copy a variable into another place in memory where I am. So these things exist. These are, if you find yourself doing a lot of host to device or device to host, though, you need to say, that's really slow. That's one of the slowest things you can do. So you don't want to get in the business, if you're writing a lot of that, or if you have that inside a loop, it's a problem. So here's some examples. The host variables are indicated with an _h, and the device variables with an _d. So we declare an a and a b on the host and an a and a b on the device. And so we allocate a pointer, figure out the size of it. So we get the size of floats times the number of fellows that we're going to have, 14. Then we're allocating the pointers, so we allocate that size floats. And this is on the host. The same thing, so that's a malloc call. The same thing on the device looks like this. So we declare a variable a on the device and a variable b on the device. So inside this loop, we get the host variables loaded, and then we copy device to host to device, and we tell it the size of the thing we're copying, and so forth. So you can basically see what the syntax looks like, and all of this is in the various versions of the SDK. Just wanted to let you see that it looks like C. What I'm really communicating here is it looks like C. Okay, so what are these kernels? These are C functions with some restrictions. And they're kind of obvious, but you just have to keep it in mind when you're programming. When you're telling the device, the graphics processor, to do something, you cannot refer back to the memory that exists on the host because there's no root. You have to explicitly move things. They always have void return type. This is one, not recursive and no static variables. So it's not entirely, these are the differences between a C procedure and a CUDA procedure. So the function qualifiers, make that go away there. So global means it can be called from the host and executed on the device. Okay, so this is a very common one. Here, if I've got a function which is going to be called from inside a kernel, so you can have a routine running on the device, running on the graphics processor, which calls another function, and it should stay on the graphics processor. Then you're in the device world. So good code is going to have a whole lot of device because you want to move to the GPU, compute there, and then when you're finished, move back is the general programming model. So all of your routines that have been declared with this function qualifier device, you can't see them from the host. They're like internal procedures if you'd made a class. Okay? And you can combine these to get both CPU and GPU code. We'll have some examples in a minute. Okay, these are a couple more of the built-ins. So anytime you declare a function, global or device, you automatically have 3D grid dim, 2D grid dim. You have the grid, the block, and the threads. Okay. So how does this work? This is whether your block. Remember, I said it could be a 1D block or a 2D block. So this is telling you the sizes, and then this is the index within the grid that you can pull out. Anytime you want to look at a certain piece of data, this is a function call which returns what you want. And similarly, the threads are inside the blocks. The examples make this clearer. Is this a good example? Okay, so here's calling one of these guys. Again, how many blocks, how many threads? This triple chevron thing indicates that it's going to go over and execute. This is CUDA, so this is a kernel. In other words, a function that's going to run on the GPU. Just said what those two were. And then the threads per block, we'll come back to that in a minute. If you don't specify something, you get ones. Basically, the key thing that I want you to get out of this is this invocation. And then know that you have automatically, if I have 100 blocks in a 1D array and I call the kernel, it's going to execute that kernel, 100 copies of it. It's going to tier them up, and let's say that part of what that kernel needs to do is get something from global memory, okay? Since there's 100 copies of it, it's got a great possibility for doing parallelism. So it will manage which of those 100 gets run when. You have no control over when the blocks are run. There's no sequencing of blocks, and there's no sequencing within the blocks of threads. So there's all these blocks, and then each block has a bunch of threads. Those things get launched at the time of the kernel, and you have to think all of that's going to go at once. Okay? And now threads get done in groups themselves within blocks, and this just gets really obscure. And this is part of the management that I was talking about. Generally, you don't have to think about this, but you should know if you try to synchronize threads, you're synchronizing threads in a small little section. We're going to do a matrix multiply in a minute, and you'll see what I mean. You're not synchronizing all of the communication at once. So if you have a call barrier in an MPI that's out on the outer level of the code, it says all the processors wait until I get to this point and then go on. Synchronizing threads is not like that. Synchronizing threads says a bunch of threads which are sharing a bit of the shared memory. They're sharing memory, that part that's called shared. They can be synchronized. So it's little micro barriers. It's not global barriers. Each kernel is invoked on the host, and the host immediately goes to the next statement. Okay? So you can have some asynchronous things going on with stuff running differently on the host than on the kernel. I'll come back to synchronous and asynchronous in a minute. I forgot what I was going to say. Right. So this is just silliness that says these built-in variables tell you how to find where things are. So there's blocks, 0, 1, 2, and then there's threads. If this was 3 blocks and 5 threads each, then you can create your favorite old running single index with the usual kind of creation. And since it's C, everything starts at 0, so there's not any -1s and all the stuff we have to deal with in Fortran. Okay, so you can create pretty easily indices that tell where the data is. Okay, here's the synchronization. So the kernel launches are asynchronous. Control goes right back to the CPU, except, of course, if you're moving data back and forth. And the threads synchronize, this is different than sync threads, will block until, so you can use that like a barrier. See, I don't want to try to teach you CUDA. I just want to give you an idea that you have multiple levels of parallelism going on here, and we're going to get the SDK out in a minute. Let's get to something more interesting. Okay, that was the end of that. Let me show you something a little more general. Now what was the magic thing? Slideshow. And then I have to play it, and then pause it, and then...
I think you can just use the arrow keys.
I don't know. Okay.
I mean, the arrow keys on your keyboard.
It's going to play. All right, I'll do it. Hang on. Okay, very good. Okay. So let's talk about the memory for a minute. We've got about 25 minutes left. You guys can interrupt anytime you want. So the GPU's got these grids, and there's all these multiprocessors. On the machine, on the device, some of you will have processors out there probably with 64 processors on your GPU in your laptop, others with 128. Some of you might have more, some of you might have less. I've forgotten what the small side is. And then each of those processors is running, let's say it'll get a block. Don't internalize what I'm going to tell you. What I'm trying to tell you is that you have no control. That's the point of this. So one of the little processors on your computer is going to grab hold of a set of threads, but depending on which year your machine was built and which version of CUDA you have, it might pick up 16 threads and do those 16 and then come back and get the other half. They really think somewhere in CUDA land, they think there's 32 threads that always go together, okay? You don't need to know that, but just be aware that they may take groups of 32 of your indices and operate on them. They may take groups of 16. All of that is happening, and it may or may not be on the same processor. So you may have a kernel which says some simple thing like y equals ax plus b, and then z equals y squared or something, okay? And you might assume that the first 16 elements of those arrays are going to be done on one microprocessor because it's one set of threads, and then the next line of the code is going to be run on the same microprocessor. That's not the way the model works. They imagine creating and destroying threads at every line, and so you don't want to be thinking my lines are all going to run the way they're arranged on the page, you know, that you might imagine. It's totally parallel. Okay, so the global memory is the piece that everybody can see and everybody can read and write to, and it's very expensive, about 600 clock cycles to get element of global memory. And that's going to be true on a lot of these devices for a while. You get about 1.5 gigabytes typically of global memory, so that's where a large part of your calculation lives. But you have to be very careful not to write code that says, we're all going to have access to this piece of memory, and it's going to change in the course of a line, right? I mean, you have to make sure that one line is not dependent. I plus 1 can't equal I, something like that. Am I making sense? I'll show you some examples that break. Okay, so shared memory is the good stuff. That's the kind of memory that groups of threads can work together. And I believe this example here has the the matrix multiply. When you're doing a matrix multiply, you could say, I'm going to take all the rows from this matrix and all the columns. I'm going to take a row from here and a column here, multiply element by element, and stick the answer into a single spot of the array over here, right? And that could be one thread's job. Every element in the receiving array could be a thread, and they all go out and pick off bits of global memory, multiply, add, and drop it into place. Do you see what I'm saying? That's going to be very inefficient because lots of threads are going to global memory, and they're just getting the same information over and over. So you're not going to ever write a matrix multiply routine for a GPU, I predict. But you need to know how these things work in a case that we can all explain so that when you do write your own kernel to do some specific thing in your code, you'll see what the catches are. So instead, if you have shared memory and you say there's a group of little threads here, there's a group, is this picture coming? Let me make sure that I'm on the right talk. What is that? These are not my pictures. Here we go. Let's do this one real quick. That's what I thought I had. So you think that'll work? I don't think that works. I think I have to do that, and then it works.
You can just use the arrow keys.
I'm doing that, though. It never moves. There's some magic bit of this and then that. There, now, you see? But I got to pause it. All right, so let's look at how the memory works in a matrix multiplication. So we're going to do the basic features in a CUDA. We'll see how we use threads. You'll see how the memory data transfer works, and we can see how it works, okay? So I think in 15 minutes, this is what we'll do, is we'll look at how something we all know how to do would look on a parallel computer. Okay, good. Okay, so this is what I was about to say. So we're going to take P, this will be the product matrix, is equal to M times N, and it's just a standard matrix multiply. So to get a single element of P, I need to take the elements of this stripe and multiply them one by one with the elements of that stripe, add them together, and drop it into that position, right? And these are square matrices, width by width. And if I don't do anything, then the thing in your head, you can say, well, one thread is going to calculate each of these little boxes in P. Everybody with me? Okay. So each element of M and N are loaded width times from global memory. So this is going to be slow. they will hide some of that latency because anytime, the way that they don't look ahead. Remember I told you that current compilers look ahead and do conditional compilation or conditional execution of lines and all that kind of stuff, and caching and stripping. Okay, the way that these work, the way that CUDA's philosophy is, they made it extremely light to start up a process. So it doesn't cost them many. In their model, if they want to do something like take 16 of these guys and tell them, go out and get global memory, okay? That's very lightweight. That starts, and while that's waiting in global memory, the compiler hasn't figured out who's going to go next. The compiler just says, oh, there's a zillion more of those, and it just keeps spinning off processes like that, one after the other. And so it needs to know that everything it's going to say can be done in any order. Does that make sense? But still, you're reading memory over and over and over, so it's not useful. So let's remind ourselves how memory is laid out. If we index it this way, this is the actual matrix elements, 0, 0, 1, 0, and so forth. In C, when we referencing things, we get this order. In Fortran or MATLAB, it looks like this. And that's going to be important to figure out where we're going from the thread and block indices. Okay, so here's how you would do it on your C processor. Okay, so this is just a CPU code. You say, I'm going to define a function called matrix multiply on host. It's going to take m by n. It's going to take m and n, and it's going to return p. And it's going to have size width. And so I loop over the indices, I and j, and do just what I said a moment ago. So we're going down here in the I direction. We're going over here. And we sum up the parts that we get from these partial sums, and that gives us the final element, which we then go over all of them. Okay? Let's do it this way. Here we're going to do the matrix multiply on the device. So the host code would look like this. It's just going to start off by saying, well, we need to allocate space over on the processor. So we CUDA malloc. We copy m over. We again allocate memory on the device of size n, and we copy that memory over. So now we've got an array of m, an array n moved over to the device. We create p, and then in a minute we'll see you have to go and calculate p, and then you get p from the device, and you free up all the matrices, and that will be the overall matrix multiply routine. Now we're going to go back and fill in what actually happens here. Okay, but you get the idea of the data movement first. And the kernel function looks like this. So this is the kernel of the matrix multiply. So we start off, we're going to have a temporary variable p-value that will store the element of the matrix computed by a given thread. Now we all have to stare at this for a minute. Won't do any good for me to say it. Oh, it's basically the same code, right? Nothing changed here, except that now instead of the explicit I and j loops that we had before, do you remember? Do I, do j, for I, for j. It's all now buried in thread index x and thread index y. And so, I don't remember which is which. The I and the j are just now thread index. And you specify all of them at once, and you just go k times, and you get p-value. Okay? So you do away with explicit loops with these thread indices. So this is an important moment. I want you to tell me you either like it or you don't. This statement is for a single block here, right? But it's all the blocks at once, because when the kernel is invoked, it's going to do all the threads. So instead of having the loops inside the process, the whole process gets run width by width times. Does that make sense?
What about the ML? Are those, you assume that they're not writing in the same memory space multiple times?
Yeah, so these are going to be local guys to each kernel. And each thread has a little bit of local memory that it keeps. I think it's 16 kilobytes, and those won't overlap. You can run out of that, and part of what we have to do here in a minute tomorrow, I'll show you that there's some, remember I told you that there's some code produced, some file produced when you compile, has information on registers and so forth. What that tells you is, have you used up all the memory on the device at any point, either the shared or the global or the registers or the whatever, constant and texture. It gives you an idea of whether you've managed memory well. So it becomes a memory management game. Okay. Now to invoke the kernel back on the host, so we have this one-dimensional, actually we'll come back to this, width by width, one in each direction, and this is the key. So we're going to launch that thing we call matrix mul kernel. It's going to have this many grids, this many blocks, and those are the arguments. And so version 1 looks like this. One block of threads, one thread block. Let me get my brain on. Right. So each thread is going to load a row of the matrix, load a column of this matrix, do the multiply and addition for each pair, and since each one is going off and getting memory, you're basically only using each piece of data once, right? You multiply that times that, that times that, that times that, that times that, add them all together. You can count. You can say maybe that's using the piece of data twice, but the ratio of things I do to the data versus the number of time, the amount of data that I have is very low here. So this is going to be pretty crappy. And the size of the matrix is overall going to be limited by the number of threads in a thread block. So this is actually a device-dependent number. Some of you will have smaller and some of you have larger. But if you say that each thread is going to do a block, you're only allowed a 23 by 23 matrix. So this is not the way to code things up. But it's the way to, I mean, it's the first way you might think, is that just assign a thread each one of these guys. Well, so instead, you start saying, well, I'm going to do a tile in here and assign that to a thread block, right? And now I'm using this bit of data and this bit of data and the stuff around it to get all the information in this tile. And I still have to put a loop around it of size width over tile width because I have to do all the different tiles, okay? But my explicit loop is a lot smaller now. And each tile, well, you declare something to be how big is the tile. But basically, you can break things up and do a tile at a time for a thread. And then here, you can have multiple blocks. So you break up P, this guy here, on the device into tiles, and each block of threads calculates a tile, okay? So every thread is going to do one element in a tile, but then I'm going to have many tiles, so that a tile is now limited, if you remember, to be 23 by 23 maximum. Maybe we're going to make it 16 by 16. But I can do all the different tiles in any order that I want, and I haven't minimized the total accesses to memory, but I've increased the amount of work I'm doing with each of the pieces of information, because anything I pull in from here I can use in all of these horizontal stripes for the multiplies. So let me show you how that works out. All of this is online, so blah. This is just what I want to avoid. Is anybody interested in this? That was a no. So there's some horrible index stuff that's dreadful in a room to look at together. But fundamentally, each thread is loading elements that it needs to do the block, the tile that it's working on. And so you've got one floating point operation for every number that you bring in. That means that you're limited to be the number of tiles times the number of memory transferred to get information in there. So you get a pretty bad floating point operation. You get 90 gigabytes per second. You're supposed to get 340. So this is one of those things where you can immediately get some speed up, but to get the full thing, you have to do one more trick, and that's where shared memory is going to come in. And you do shared memory. I already showed you this. You can review this on your own time. Actually, this is useful to see real quick. So here's the different kinds of memory. There's local, shared, global, constant, and texture. Okay? Shared is on the actual processor, the chip, and all the other guys are off the chip somewhere else on the board that you plugged into your computer. And just be aware that there's, in this lecture that I'll stick on the website, on the wiki, you can keep track of all these things. Okay? This is very important. So a register is dedicated in hardware. It's very, very fast. You can instantly get information. A register is like the index of the block of the thread that I'm on. You get that very, very quickly. Shared memory is something that we're about to talk about. That's very, very quick, and a group of threads has access to shared memory together. So we can declare a little bit of group where we're going to share information. Those guys can share, and the others can't see it. Local memory is slow. Global memory is slow. Constant memory is actually slow, but it's very well cached. And so you can assume constant memory is actually fast. And texture memory is the same kind of way. And then instructions themselves are hidden from you. But here's something fun about these chips. If I haven't dissuaded you yet, we wrote code for the GPU to do a problem, and we ran out of memory because the code was too long, not the data. Isn't that nutty? How does that happen? I just couldn't imagine that happening in a CPU world, but that happens on a GPU. Okay, so we already did this part. We did this. Okay, so I'm trying to finish up. So the idea is basically you can use this extra layer of memory to, so we went off to global memory and we got, let's say, this stripe here. We're going to do a tile in here, or we're all adults. We can pretend this whole thing is a tile if we want, right? It all works the same way. So we've got this stripe of data here, and we're going to need it to get this point by multiplying it pointwise with that stripe. And let's say we got this stripe, and we're going to need it to multiply with this one and this one. So if we can save all of that data in shared memory and use it for all the horizontal stripes in my tile, then I've reduced the number of calls to global memory, and I've got it held close to me in shared memory. Okay, does that make sense? It turns out if you actually do that in your code, again, you'll never write a matrix multiply, but you need to be thinking of layers of memory, then you will get much, much better performance. And the way this goes is, I guess I didn't put the number on here. Actually, this is not my slide, so, you can get all the way up to the machine, to the device speed. So you can get your 390 gigaflops on the G80, or on a Tesla, you can get up to a teraflop. So you can do quite well if you do this. But what you have to watch out for is that the shared memory is big enough to hold all the numbers in the column that you need. And so what I'm trying to impress on you is you don't think about what you do to program these things is you're thinking about how am I managing the memory. It's just all day long, because the only slow thing to do is to move memory either from global into shared, or keeping track of the 64K. I mean, this is like programming for an Apple IIe. When I was little, you get 64K in your little local memory, and you have to manage it. It's not like the cache, which is automatically managed for you on a current CPU. So it can be hairy. All right, I'm going to let you read this on your own time. The bottom line is that it doesn't look bad once you've coded it. This is the whole thing. So this whole thing is the matrix multiply tiled so that it runs screamingly fast. And I think if you stare at it on your own, or if we talk, I'm going to be here for the next few days. We can sit down and talk about this one-on-one. So you declare some shared variables, right? And these are the temporaries for the M and N. So that's the parts that I'm going to read off for M and N that I'm going to use in my tile. And then I've got my threads and blocks and rows and columns. I loop over the tiles required to get this element. So I've got a loop here. And then bring what I need into memory, calculate these guys, do a quick synchronization of the threads. We'll have to come back since we're out of time. You want to bracket critical information between sync threads, so you do this. Here you actually get the value of p-value that's going to come out, and you can spit that out into the total array. So we'll go back over this in some detail with the dedicated few that make it to the next meeting. Here's the effect that you get in performance. If you didn't do anything, you get 10 gigaflops. If you tile and you didn't do anything else, you stayed at 10 flops if you used very small tiles, okay, because you weren't, you're still going to global memory too much. If you've got big enough tiles and you do all the tricks that we just described, you get huge increase in performance. So what does it mean? It's just the meat on the bones of all your time is spent thinking of how to manage memory, because that's where all the performance change is, a factor of 9 or 10 in performance based on how you dealt with memory. Okay, so I think we'll stop there. We still have, actually we're out of time, so anybody have anything you want to talk about before you go? Yeah. As opposed to double. Yeah. This is a rapidly changing area. I looked in about 3 months ago, 8 weeks ago, and the statement was that the new model was radically better, double or triple the performance for double that it had been. Effectively, they had special hardware. For a while, there was no double precision at all. Then it seems to me it was about 14 months ago and the cell has had double precision for some time. About 14 months ago, NVIDIA put a double precision, but it was effectively just a few of the floating point elements could do that. And so it was like you had very few processors on chip to do that, and it wasn't very fast. And they're rapidly improving that situation. So my view has been to do my calculations while I'm learning how to use these things in single precision, and assume that by the time I know what I'm doing, there will be a full double precision, full performance. And I think that's right. I think soon that'll all be fine on all the brands, whichever brands you want, because they all have to compete and win there. You have to think about what does the market want. If they really want to do this, they'll all have to go there. Yeah. Which features of what? Okay, so I've gone through that exercise. The question is, if we had access to the NVIDIA design team, what would we tell them to change first? Okay, so in the order of questions that I've asked them over the last 2 years, the first thing I said, I was going to count with this finger. The first thing I said to them was, you ought to, so they were selling the chips, and they were not giving you clear instructions on how to build your own Beowulf. So we bought 4 or 5 or 6 chips and burned out several power supplies and went through lots of trouble. And so the first thing you do is you say, if you really want us to put several of these inside a box, and they're all going to run at 275 watts, then the power supplies, which are nominally rated, whatever wattage they are, actually most of the power supplies that you have that you're building hardware out of can't deliver steady state what they say they can, because they've never had to, because none of the hardware ever runs at the rated power capacity. GPUs do. So you start burning through GPUs. So one of the things I requested was a clear suggestion of how to build my own cluster. And they said, buy a Tesla cluster. Well, okay. So that was a little bit disappointing, but that, it's not their job to build my cluster for me. So that was a simple thing. What will we change on the chip? The second thing is much higher order library calls. Now, I've tried to dissuade you a little bit because I want you to understand that it's a pain in the neck to try to program in detail for these devices. On the other hand, if you can and that's if you really want to write your whole code in graphics processor language. But if you can work at a high enough level, and I'll show you the example tomorrow at a higher level, if you can work at a little bit higher level and just use library calls and maybe write your own library call for 2 or 3 functions, which is what I've been able to do for one example, then the whole thing is beautiful and you get your rapid high performance. So what I want, the second thing is, it's not answering your question, but from the company, more high-level calls, please. Because this stuff that we're looking at right now, you need to understand it. You want to know that memory management is key to the performance, because that's not going to go away, but golly, you don't want to write a program like this very much if you can avoid it. The final thing is I wanted to see a lot more memory per chip. So if they told you you could have 100 more processors, or I don't know the appropriate size, or another gigabyte of memory, these things are so fast that no more processors, please. I want a lot more memory. And then the size of shared, local, register, and global memory would all be larger, and I would not be forced to look at the register files that get written out at compilation time and say, oh, I'm running out of room to do what I want to do. That's a fairly, it's very straightforward. It works. I'm being negative. As a physicist, I do not want to do computer science, right? And so I find it frustrating that it's still at a kind of low level where I'm managing how many bits and bytes of indices I have. On the other hand, it works great, and as soon as they crank up the memory a bit, then I think we'll all, just like in the regular devices we use now, we won't run out of memory, and it'll be much better. So the first thing I would do would be to add memory, the short answer. And the other thing is, what we haven't gotten to is the difficulty here. If you can think of a problem that fits in a gigabyte that you need to do very quickly, and there's some examples in the room that I've already talked to some of you. There are some wonderful physics and astrophysics problems that fit in a gigabyte and need a lot of calculation on that small data set. Those are perfect for this device. But the typical problems we have are hundreds of gigabytes of data that we need to process if we're looking at turbulence or evolution of a large object, a complicated multi-scale structure of some kind. And that means you need lots of GPUs. And so the communication between GPUs needs to be faster. It's just very slow right now because if I'm a GPU and you're a GPU and you two are the hosts, if I want to give you a piece of information, I give it to my host passes it to your host, and then he gives it to you. So there's no direct line of communication, GPU to GPU. And that's fundamentally just a deal breaker for production line. This is gonna be the winning technology, but when you try to use, when you want to do a petaflop calculation, you must have solved that problem. So it'll be very interesting next week to see what the Friday speaker says. That's the thing to ask him, is how did you manage the communication and the memory? All right, let's take a break. No clapping. This is a workshop.